Welcome to the ACIT Science Podcast, the official podcast of the Association for Critical and Interdisciplinary Thinking. We are a global nonprofit organization dedicated to spreading education around artificial intelligence, neuroscience, and social change. In this podcast, we are hoping to provide insightful discussions with young professionals and world-leading researchers alike. I'm your host, Manuel Brenner, and now without any further ado, let's jump right in. I'm here with Charel van Hoof. Welcome to the podcast.
Thank you.
Just as a short introduction, who you are, what your background is. You hold a degree in computer science from Delft Technical University, and then also made an MBA from Rotterdam Erasmus University, and you are now doing your PhD. But in between your PhD and your studies, there lies probably a longer and more eventful period than from our previous guests and also the average PhD student. You were senior vice president and CIO at international companies like Philips, and you are also an advisor and investor to startups, and currently working as transformation executive at Volvo. So you have a background in the business world and are also experienced in like the digital business components and like the role information technologies play in the modern business world. And considering AI is a huge information technology, we will also get into more detail later how AI is shaping the modern business world and what influence it has on the economy and these kind of things. But at the same time, you are currently doing a PhD in artificial intelligence and robotics at Delft Technical University. And this is probably the reason we are in touch, and we have this common shared interest in AI and intelligence. And I think the scientific perspective on neuroscience, intelligence, robotics is something we can spend a lot of time talking about. So I think there are these two main roads we can take, the scientific perspective and the business perspective. But before we get into that, just as a general question, what motivated you to get back into the university and start a PhD after all your experience in the business world?
Yes, very nice question. Well, actually, then I have to tell a little bit about my history, and then it falls nicely into place because actually I was one of the first students in the Netherlands for information technology, and I was the let's say that generation that got a home computer at home and a TRS 8010 color computer. Which of course was fascinating for me at that age. And of course, at that time, I didn't have the money to buy any games, so I had to make them myself. Amongst others, for example, I programmed Pac-Man and had great fun with it. Then, of course, after I finished high school, I went to the university and study information technology. That was a very obvious choice. And indeed, as you refer to, after that, I went working, and let's say after a couple of years in my career, I also figured out that I wanted to have more business language and background knowledge to basically exploit all the great opportunities of IT, also in a business context setting. So I did my MBA at Erasmus University in Rotterdam. But to be honest, I always kept that let's say let's say passion for information technology, programming, and all the amazing capabilities that came out of it. So, and after a couple of years, the whole artificial intelligence came to fruition. And of course, when I went to university, there was also some form of artificial intelligence, but of course, that didn't contribute too much yet to the world. But in recent years, I saw, to my delight, that let's say there was a whole new energy coming from this artificial intelligence technology into the world that started to fascinate me. So I started to explore with it, and in my free time figure out basically one of my first neural networks that I programmed was a reinforcement learning to win, of course, Pac-Man. So I complete cycle. And basically I was hooked. I thought, hey, this is really really interesting. So I tried out all the type of neural networks, etc., etc. Got deeper into it, but also at a certain moment I figured out, like, yeah, more data, more compute power probably will get a little bit more results, or still fantastic results, but it is not the breakthrough yet in true artificial intelligence. And that's when I got, let's say, and at a certain moment I had the opportunity to combine work with a PhD. So I grabbed that opportunity and started my PhD at the university at Delft, part time, in combination with working, in that case indeed at Volvo Cars in Sweden. So for me that was ideal. I could combine my passion and combine it with actually using information technology and AI in a business context as well. So yeah, that worked very well for me.
You mentioned that more data doesn't necessarily give us more AI or more intelligence. So that whole vocabulary, that whole term intelligence is still highly disputed. And you say that to get to true general intelligence still requires a couple of steps. So maybe as a very vague starting question, what is general intelligence for you, and what makes intelligence special?
Actually, I don't know. I'll just follow the definitions that I see floating around in the various papers and the various books that I read. What I do know, and basically, let me take the example back to the Pac-Man learning. Of course, when I trained 20, 30, 40, 100 million game screens, I noticed, of course, that Pac-Man was great in clearing the first screen and the second screen, but at the moment I hit the third screen with a new maze, it simply bumped straight into ghosts. And for me, it was clear the algorithm learned to recognize pixels, but had no clue that a ghost actually is dangerous. So
Okay.
it didn't generalize, I think, is then the terminology in AI that is often used. But I started to figure out that it is not just, there is more to it than just remembering pixels and see the, let's say, yeah, the relationship between pixels. So that caught me, yeah, thinking on, okay, what is it that I need, I want to do more. And of course, like in many technology advances, you look to nature to get your inspiration, and then you get into the wonderful world of neuroscience. And yeah, there I walked into the, let's say, active inference or free energy principles of Karl Friston. Actually, it was my professor Martijn Wisse who pointed that out, who was making that link. And for me, that made complete sense because the more I read about it, the more I thought, well, I think it's a very good point he's bringing forward. So I do think he has a handle or an insight or a possibility to the next to really true artificial intelligence. And I think it's good to have a neurosciences framework as insight of the principles that you apply. So I'm a software architect and of a software engineer, programmer, architect, whatever you want to call it. But basically, I learned in my career that if you want to do large IT programs like large SAP implementations or whatever, pick one, something that costs 100 million plus. One of the first things I learned, of course, to make really sure that you have a good, well thought through architecture. And then the architecture concept in this artificial intelligence world, of course, I think is neurosciences, where they have some great ideas. I think that could be worthwhile to explore further. And yeah, I think that's when I stumbled upon the fantastic world of and work of Karl Friston, and yeah, I got a little bit hooked to dig into that subject.
Yeah, it's interesting that from an engineering perspective, creating intelligent systems almost seems a bit unbelievable. but considering that we, in the form of brains, already have intelligent systems around us, it seems good advice for the AI community to just look to neuroscience for inspiration, because what we consider to be general intelligent systems are human brains. So they have to work on some principles that could be useful for us to also apply in the way we shape our algorithms and build our architectures. So Karl Friston's free energy principle is causing, or has caused, quite the stir in the AI and neuroscience community, but it's also famously difficult to understand, especially for laymen. And um, so maybe we can try to make the free energy principle as approachable as we can in this short period of time. We have both also written about it online and tried to popularize it. You also created these Kaggle notebooks, trying to explain free energy principle for people without a PhD. So how would you explain free energy principle to someone without a PhD or without a background in AI and neuroscience?
Yeah, indeed, you're absolutely right. So imagine, I've been working and let's say in all kinds of business concepts and in executive boardrooms, and then I had to go back to actually understand integrals and probability theories and God knows whatever. So I can tell you the first times I tried to read these papers, it was quite scary because I actually had no clue at all what was all the math doing over there and why it would be correct. So I had to let's say reintroduce myself to all these type of concepts and learn them again. Partly, of course, I've done somewhere in my past, but I can tell you if you have not been applying all kinds of mathematics the last 20 years, it's not that easy to recall it back. But there's a good thing nowadays that I didn't have when I was studying, and that's called internet and YouTube. So fascinating how much you can learn from simply Googling and, repair your bike until repair your washing machine, but also how to do very difficult integrations. You can learn
Right.
it now all on the internet. Just click on there, follow a couple of these videos, and let's say you actually can do a lot for yourself. So I just started to dive in and dive deeper and just hold on and read many of his papers in parallel. That is, read until I got stuck and then try another paper until I got stuck. But then I found clues in other papers again that, let's say, unhooked some other stuck elements in other papers. So by reading them in parallel, I got step by step a little bit further in understanding. And of course, I had great help of the university with other colleagues and friends over there that was also digging in and trying to understand step by step more of the theory. And but I also promised myself, like, yeah, let's try to write it down because I think this deserves more attention. There is, let's say, that there is something in his theory or framework of free energy principle that is correct. It is the a link to true intelligence, in my belief, but the learning curve is quite steep. And of course, I had these special circumstances to have a business background, and there's this running joke about executives that if you want to tell something to an executive, you have better make it very simple, else he doesn't understand it. So I
Yeah.
thought, well, let's try to write down. In this case, I use Kaggle notebooks to write it down in such a way that I could understand myself when I would be reading this for the first time. So I did my best to write down indeed the free energy principle in a digestible way. In less in the math language and more in the English language to go step by step, understanding the let's say the concepts. And yeah, in the end, I truly believe it's mathematical rigorous. So I understand all the logical steps. It is biological plausible, at least what I can see from my limited understanding of neurosciences. But of course, I see all the references Karl Friston makes and many other people on how it could work biologically. I think that's very good, but also I think it's evolutionary plausible. I think that's also a very strong, let's say, part of the whole concept that I understand which logical steps could have been progressing over the evolution to let's say to come to this level. And this theory of the free energy principle, let's say, relates very nicely to it. Your question was also, please explain a few words. That's kind of hard, but if I would try to give it an elevator pitch, I think a couple of cornerstones is in this theory, and one of this is what I call the predictive mind or the predictive brain. So the concept is that the brain tries to predict all the things that's happening. And as long as the prediction is okay, it works fine. But if the prediction is wrong, then other hypotheses start working in your brain to try to figure out what could explain the let's say the delta or the prediction error of what you thought that was going to happen and what's happening. I think that's the concept. That's a strong concept in it. In for machine learning people, basically because we're not talking about one-off predictions, but we're talking about sensory streams of neuronal information flowing into the brain, or sensory information. Basically, you have the opportunity to start predicting the next thing that would happen, and by that you have an let's say you don't have to label all your let's say inputs. It's basically you try to predict the next let's say video frame in a video, or the next sound bite in the sound. And that mechanism, let's say, results in not only that you start predicting it, but that you also start understanding or start to generate more abstract time invariant concepts around it to start better and better predicting it. E.g., if I roll a pen over the table, the pixels that are, let's say, on my retina, of course, there is a natural law that the pen does not suddenly, let's say, disappear or fall apart. So the pixels keep together, and it's that type of things of the natural world that the brain started to learn, and let's say start to incorporate. And in the end, the free energy principle or active inference, as I like to call it, that minimizes the free energy, is dus about prediction error minimization of both, let's say, the sensory inputs and the, let's say, the hidden states that could cause that sensory input. And that's the basis of the network. And there's a lot of very interesting math behind it. But after you follow all my notebook, it all turns out to a prediction minimization scheme, which is sometimes called also predictive coding. And yeah, it's very interesting to see that it all works.
Yeah, I think a crucial cornerstone of the free energy principle is really these the internal models of the world that the brain has, and these implicit assumptions about the way the world is and behaves, and the way the world could develop into the future. And this always necessitates a certain understanding, a certain model within the brain that can understands how light falls, understands how things move, and you can apply that to a lot of different things. And these models can also be hierarchically structured in the sense that you can have, on a very basic level, you can predict the way that the pen rolling over the table is kind of a coherent structure that is moving in a certain way and will look the same way. But you can move certain levels of abstraction up until you can see that the brain implicitly knows that there's something like countries, and then that there's Europe and the world and the universe. So we, as human beings that are constantly getting information from the external world into our brain and have to kind of pass through this information to create a model of the world, we have to can use then these models to understand both the input that we get, but not only leave it like that, but then predict the future state of the world based on this. And you talk about the free energy principle as minimizing this prediction error. There's also this term called surprise with
Yeah,
relationship to that the free energy is basically a measure of surprise. Can you
correct.
can you explain a little bit how that fits in together?
Yeah, no, exactly. And let's say I was also a little bit puzzled always about why is it called free energy and why do you want to minimize it? It's. I'm Dutch, so my first reaction was it's free. Why do you want to minimize it? Of course, that's not the right connotation. Let's say so. Free energy, if you roughly translate it to surprise, then you're minimizing surprise. Hence, prediction error minimization is the connotation, is then the logic. And that goes back to the point that you make. You start predicting, and the better you predict, the less the surprise. And hence you have prediction errors that flow down to into the, let's say, to the areas in your brain where you receive all the sensory inputs, and upwards or front of your brain goes more and more higher abstraction levels of the interpretation of that sensory data, which is typically also what we see in neural networks. You see first a picture of an elephant, and then the next layer see contours, and then the next layer start to shape a concept of like an elephant, etc., etc. Similar, like let's say that type of concepts sit also in the free energy. Also, what I try to do is every time bridge in my mind and compare it to artificial neural networks, because of course that's a concept more and more, let's say, people understand, and as a rich a group of data scientists and machine learning people, and etc., etc., so people can relate to that framework, and I try to understand what's now exactly the difference between an artificial neural network and a free energy or an active inference network. And indeed, both are hierarchical and etc. etc. But a couple of differences that are interesting to explore. Because, for example, one of the differences, it's called active inference because it's got a component that's important, and it's called action. And a traditional or first round artificial neural network doesn't have that. And I think that part of action is a very important part. Let's say that actually was the starting point or the birthplace of intelligence, with this very simple logic that because very simple, let's say, early beings, ancestral beings. No, that's not the right word, not ancestral, but let's say the beings, very primal beings. Of course, when you have the capability for action, of course, the next thing that you want to do is have an insensible action or a good action that actually improves your chances for survival, and that drove the starting point of let's say the need, the necessity to actually build a model of the world, the generative model we talked about, to start learning that concept. That started to learn the let's say that spiked the need to yeah, to build models of the world to better actually understand the results of your actions. And I think that also correlates very nicely with the work of, and I hope I pronounce his names right, but Georgi Bushaki, which also pitches that idea about, let's say, action being the centerpiece of it all. It's the action perception loop, not the other way around, was his argument. But I think there a number of elements come together, and I'm also fascinated that in the free energy principle, or the active inference concept, that the action part is so prominent in place.
Yeah, that action plays such a prominent role because in the free energy principle, you can maybe think about it in terms of you make predictions about the state of the world, and if your prediction is not something you want to see realized, then you can act to make the world actually be that way that you predicted it to be. So it's a way of minimizing surprise in
Yeah.
that equation, is to just do
For
it
me,
by
there was
acting.
a indeed for me there was a kind of aha moment. So the concept, if you want to move your arm, it's not an engineering principle that you can start calculating the muscle strengths. It's the other way around. You predict that your arm is up, or whatever it is where you want to have your arm to be, and then let's say by moving your arm, you actually start fulfilling your own prediction. That's a little bit the concept behind it.
Yeah, and with respect to this inside-out approach that Buseki talks about, it's quite interesting to see that with if you get a fake limb, for example, after an operation, a robot arm basically, that your brain that is just attached to your nerves in your arm, then people will pretty quickly figure out how to operate that arm just based on trial and error, because you don't really need to know from first principle how do you move this arm, but you just the brain is really good at just trying out certain signals and remembering those that led to fruitful action, to useful actions, and those that actually, like in that prediction frame, if there's an action that leads your arm to come up and fulfill the prediction of having the arm actually being up there, then it's successful and it minimizes surprise. So then it's stored as a useful action. And so you can actually make use of the fact that, yeah, you don't need to tell, like, hard code each fake limb based on deep understanding of how the brain codes, but the brain will figure it out on itself, basically.
Yep. Yeah, and we tested that at the university in Delft also with robotic arms. And if you see how they move, I vote they move quite naturally. Let's put it that way. So, of course, that this is not a scientific proof, but it looks quite good.
Yeah, that whole action aspect also fits in nicely to the point of artificial intelligence and robotics institutes actually collaborating closely or being at the same faculty, basically. And so
Yeah,
how does your work? Do you actually work together with roboticists, or how does your work tie in together with what
yeah.
they do?
At the TU Delft, I'm part of the department called Cognitive Science and Artificial Intelligence. Sorry, Cognitive Robotics and Artificial Intelligence. So it's a robotics department. So, and it was not a coincidence because I believe that, like many others, that part of that breakthrough that we need is to apply this into kind of robotic environments because they closely mimic the real world environments that our brains need to operate in. So as long as I've given a simple MNEST example for a neural network to learn, it misses the complexity of the real world. And I think the complexity of the real world is the key also that you need to get a breakthrough in true artificial intelligence. And I can tell you, by the way, I'm also part of a robotic soccer team, and I can tell you there is a there is a there is a vast difference between all the beautiful concepts that you invent on paper or do in a simulator and then what you see happening in the field. It's vastly different, I can tell you.
Yeah, true. I mean, nature didn't have the luxury of having animals just die out. So it definitely has to work, and nature can't really start with pen and paper and figure out a beautiful, like, conceptual framework for developing the algorithm. But it has to work, and it has to be able to adapt quickly, or it just dies out.
Yeah,
And I think it's maybe also one of the interesting key aspects of the free energy principle, that it's connected to evolution and connected to, like, how living systems actually operate, and this whole idea of this predictive brain being integrated into this Bayesian framework, and in the Bayesian framework there always being a measure of uncertainty. So there's like these two big approaches to statistics. There's the frequentist and the Bayesian approach, and the Bayesian approach really actively incorporates prior knowledge and actively incorporates uncertainty into your approach to the world. And I think this is, from an evolutionary perspective, like a really key idea to model a being acting intelligently in the natural world, because there's always like a limit to what you can know about the world, and there's always like a huge limit to what you can predict about the world. So there's always this measure of, you need to be able to react to different circumstances and really have in your model of the world this measure of uncertainty.
Yeah. I fully agree to that, or the what I call the lazy brain principle. I mean, there's so many signals that the brain could react upon, but somehow we have a very good filter to understand what part we want to react on and what not.
Yeah, and these filters are also part of these like Bayesian hierarchical frameworks that really you make a prediction and have a prediction error about um, the input you were expecting and the input you got, and if that prediction error is not too large, so if everything is going according to plan, according to expectation, then certain elements of your brain don't really get triggered, and you don't really. I mean, we can also talk about attention and consciousness and how that relates to these ideas about intelligence. But in that sense, in these hierarchically structured predictive frameworks, then you don't need to worry about most of the input you get into the brain, most of the information you get into it. So
Yeah,
you kind of have the luxury of being lazy, as you said.
yeah.
So how would you relate the free energy principle to this evolutionary perspective, or maybe I don't know how deeply you went into the relationship to thermodynamics and why it's actually called free energy and where that term comes from and how you can
Not
understand
not
this comparison.
not too deep, although I understand the let's say the argument and the concept. So indeed, free energy actually goes beyond artificial intelligence, right? It's a principle of everything around us. If I follow the logic of Karl Friston, let's say intelligence is also a product of it, or let's say maybe even a byproduct. Who knows? So he has some very interesting podcasts, also done where he explains that. I will not try to repeat his words, but he indeed there is a core. Yeah, this is a sort of mathematical law concept or principle that's at work in a broader picture, and hence also let's say artificial intelligence or intelligence, sorry, is a logical result of it.
There, besides the free energy principle, which is kind of the overarching theory, there is also a couple of other really interesting aspects to intelligence. One we have also already talked about is the relationship of spatial thinking to intelligence, and maybe also kind of an evolutionary perspective of how intelligence could have arisen from spatial thinking. Can you explain a little bit what these relationships might be and
Yeah,
where they could
I
come
think
from?
yeah, sorry. No, I have a concept in my mind, and let's say based upon many papers that I read and also many books, and I think the let's say the storyline is like this, and I think in the book indeed of Buzaski he has written it, but I think it's also mentioned in the book of sorry all the names Barbara Tversky. I saw there as well, and I buy into these type of concepts. So I think there are evolutionary steps how spatial thinking is the basis for our intelligence, and that started what we discussed earlier with action, and action leads to you want to do the intelligent actions to actually increase your chance of survival, which creates the need for a simple brain. Then the next logical step you can imagine is that if you have action you can start moving, and then with moving you get concepts as debt reckoning and other things that basically debt reckoning means basically if you move a certain time and you have to go back to where you came from, what even ants can do and many other species, and we also know it as humans. We know how to go back where we came from, to a certain extent. To a certain extent. To so somehow you have let's say, a SLAM mechanism in your work, using some terminology from robotics, simultaneous location and mapping. So and that's also what the place and the grid cells do in your brain. It's recognizing places around you, and it's let's say, so the mapping part and the localization part is understanding how your head is turned, and if you move to the left or to the right, that you understand that you can go back. So that combination is also what we use in robotics to drive your robots back, or understand where you are on the map, and drive your robots around autonomously. That type of concepts is also grid and place cells. And then the next level, of course, is that you can imagine that, let's say, you not only use it on physical objects, but also on non-physical objects, so imaginary objects. So then you get these concepts also of distance, and something is more or further in the abstract world. And then it's an easy bridge to, let's say, to the last layer, as Burzowski positioned it, that you can start pretending or imagining yourself doing actions, and the results of those actions, in the, let's say, in the future. So you don't have to do it. So the crucial step between the previous step and this step is, in the previous step you actually had to do it to predict your result, and now you can imagine that you can do it, and then you can still predict the results. So those are the logical steps they pitch, and I buy into how intelligence could have emerged. Um, but it all started with the action, and the need to do a sensible action to increase your survival rates, and then predict your own action. And then you got causation also in the mix, because it's an action has a result, and then you start predicting results, etc., etc. So it's, let's say, I didn't prepare a pitch like this, but it sounds, it comes together, right? I mean,
Yeah,
I
yeah.
can follow that logic, and so I buy into that type of thinking.
I mean, what also underlies this is the idea that nature is really good at recycling certain structures that are already existing in the brain and just recycling them for different, more sophisticated uses. And it's pretty clear that really, yeah, abstract thinking, mathematics doesn't come out of a vacuum, evolutionary speaking. So there has to be some kind of structure within our brain that has a more pragmatic need, like you mentioned, dead reckoning for ants, finding your way back home, navigating in three-dimensional space. That's a task every single animal has to fulfill to a degree. Really understanding distances in space, it's all really crucial. And then you have in the hippocampus and the entorhinal cortex these place and grid cells that can already encode this kind of information, and then through some like random act of evolution and a lot of time passing, you suddenly start to the brain starts to figure out that you can actually encode different kinds of information with that, like abstract concepts, for example, and use the same kind of structure, the same kind of language to think, this apple is this size and this apple is larger than that, and then there's a spectrum between them, and you can say, like, this apple is more close to the one apple than this apple to the other one, or like pretty random example with the apple, but we can think about the world in these kind of concepts, and we can abstract and compare things to each other and understand similarity and understand difference.
Yeah.
I think there's really good reason to believe that that's rooted in spatial thinking. And it's also really interesting to think about, like, the queen of science, of all abstract thinking, mathematics, that some people also claim that, like, every mathematical operation you can do, it's pretty obvious with summation or multiplication. You can just have like a couple of coins on the table on one side and a couple on the other side, and then you put them together. That's an operation in space which equates to summation. But you can also move up levels of abstraction and still always have kind of an underlying action in the world that's underlying every mathematical thought, and thereby every like abstract thought you can have. I think that's like a cool story you can tell.
Yeah. And but also then the other side of the coin, maybe also good to relate to that, because there are some really strong concepts from neuroscience. But if you look at the pragmatic results, I mean, we got daily success stories of artificial neural networks, let's say, making next headlines in breakthroughs. While, of course, with the strong concepts in, let's say, coming from the neurological, let's say, papers, they're still stuck with papers and more difficult math. And that's also why I started to write the free energy without a PhD, because I believe that there are some really strong concepts in there that should more and more people should know about it, and that's why I published on Kaggle also for machine learning and data scientists, in order to stick their nose into it, in the hope that more and more people get interested, and more people start to also marry the concepts of neurosciences with the artificial neural networks. And somewhere there, I believe there hopefully is a next breakthrough to either let's say maybe simplify let's say active inference more back to the basics of a simple neural network, or the other way around, bring some of the neural active inference concepts into the neural networks to actually create a more complex but also more powerful or capable, let's say, capabilities or use cases or results. I think somewhere is an interesting field to further explore, because the way I look at it now, I think that neural networks are a special case of an active inference network. They are, let's say, they are a simplified version, and the active inference brings more richness to it. And we talked about it, about the action part, for example. But also, I think one of the main differences is that if you look to a neural network, it's one way. If I do inference, it's one way from bottom to top. But active inference with prediction, it's two way. It's from bottom to top, from sensory signals to invariant concepts that give meaning to something, but also the other way around. The prediction is coming down, so the prediction is getting into the mix as well on each and every level. So I do believe that neural networks are a simpler case of active inference. Of course, many people can argue with me that I'm, let's say, overseeing things, and that I might be wrong. I might even be, but that's a little bit what I have in my mind. So I'm carefully trying to understand it also through the lens of the success stories of neural networks, and see how active inference might benefit from that, or the other way around. So I think that's also a little bit my pitch for more people to simply go out there, read about active inference, e.g., pick some of your, let's say, publications, Manuel, or my Kaggle notebooks, but start reading about it. I think it's very interesting theory that indeed might hold the key to true artificial intelligence.
Yeah, there in the AI community, there seems to be this, like, based on the huge success story of deep neural nets and CNNs and these kind of architectures that are really have changed the entire landscape in the last 10 years. There seems to be something profoundly lacking behind their basic ideas, the way they can. I mean, there's people that hope that just scaling up these architectures will get us more intelligence, and like after the famous more is different, just getting more data will provide a qualitative difference and make something more intelligent emerge. But I think there's, like as you say, there seems to be something substantially lacking behind that, and that needs to be a more, like, maybe we also talked about the danger of following a more principled approach, because principles can sometimes break down in the application cases. And as has already been famously in the first AI winter, where no one believed neural networks could actually work because people showed from principles that they couldn't work, and then just trying it out and engineering them and just training them with a lot of data suddenly seemed to work perfectly well. I think there also always needs to be this trade-off, but I think, like, especially looking at neuroscience, as you say, and looking how could the brain work, like what are the principles human intelligence works on, and really look at that and be inspired to think how can we change the architectures that we program every day and that are starting to really shape our civilization as well.
Yeah, and the core of active inference is a dynamic system. So it's motion, inertia, or whatever you want to call it. That's let's say, if I make a link to neural networks, that's part of a neuron. And I think that's important, because the world and our brains, of course, are intelligent because they start to understand the world, but the world around us is shaped on spatial and temporal, let's say, truths. And the fact that active inference has that on board in its native design, in the core, let's say, I think it's an important argument why indeed this could be the, let's say, next leap into true artificial intelligence.
Hmm. How far do you think we are away from getting these kind of true or more general intelligence?
My opinion, I still think we're far away. We just start to unveil little parts of it, and I don't believe that there will be let's say, sudden breakthrough that tomorrow there is something, or next year, or coming years, or whatever, decades. I think we're still, let's say, far away from detecting it, and maybe it's a good thing.
Yeah, maybe. I think there might be this interesting correlation between how strongly people look at the brain and at neuroscience for inspiration. Because if you are in the world of deep neural networks and see how well they work, I think it's easy to get kind of maybe a bit arrogant, even with like in your faith in how much these architectures can achieve and how close we are to general AI. But if you look at the brain and we really see how little we understand of the brain, how we don't even know the basic coding principles, how to really extract the necessary information from fMRI data, from EEG data, from spike trains. I mean, there's a lot we know, but we
Yeah,
don't really have a big kind of vision of what's going on there, and we are really very far away from understanding our own intelligence. So that's also my intuition, but I think that's something that's not really coming from the AI side, but more from the neuroscience perspective. It gives a certain humbleness to what we are doing.
yeah, indeed, and I also believe, to your remark, that empirical results will drive us forward. I don't believe that more difficult math formulations will help us. I think we are probably looking towards, the same way that neural networks were born, in the sense that it was the practical results, and the math needed to follow, and I still think we're falling short in even the correct mathematical language that we need to try to express what's actually happening in a neural network. And that's even a simple, concept compared to what a full hierarchical dynamical system like active inference is proposing. So I do believe that indeed empirical results are the next step.
Yeah. So talking about like empirical results and connections to the real world, AI is really already shaping the business world quite substantially. And maybe as a general question, based on your experiences also working in these big companies and having to react to advances in technology and also seeing the opportunities behind that. How is AI and big data kind of shaping the business strategy at the moment, and how businesses operate?
I think most businesses, in the meantime, as we say it in Dutch, the quarter fell. So there is everywhere the aha moment, like, okay, this is determining our future. I think some companies earlier than other companies, a lot of business opportunities because it's dramatically changed the whole competitive landscape. So massive interest, of course. Data and data analytics, etc., is an older occupation, already known in these companies, in many companies, and let's say often used to let's say to generate insights from data type of missions. But of course, having worked for a car company, it's far more than just generating insights. It starts. It is in the core, of course, of the future of autonomous drive. As you can imagine, there's a massive amount of interest. So, and that's not just simply departments anymore. That are strategic alliances that are let's say, starting whole new companies with massive investments in engineering and capability, etc., etc. So the let's say if you're a student and you're studying AI, I think your future is bright. There will be in the foreseeable future many demands to knowledgeable people that have insights in this and can contribute because again it's still I think if I can compare it, we're still at the start of the industrial revolution. It's this will not stop. Let's say very soon. This let's say gigantic increase of capabilities will only continue to mount.
Hmm. Do you think in a different way the current AI technology is also a bit overhyped, and like everyone is trying to jump on the train but doesn't really have actual uses for this technology?
No. Let's say it's overhyped. So if people start yelling, tomorrow the world will go down, I think that will not happen. Of course, it has a dramatic impact on our world already, and there are some very interesting series or movies published about the impact of AI on social media, and then the impact on people, where you can also already see happening how artificial intelligence optimized to drive profits of tech companies might be upsetting or let's say being problematic for societies. So yeah, active inference is already massively changing our worlds. So I think overhyped. I understand why people saying that. Yes, we expect, let's say, too much in the media, but be careful in the meantime. Things are really changing fast,
Yeah,
my view.
yeah, I definitely agree. I mean, it's currently also been thinking about or I listened to a podcast about these deep fakes, this media that you can artificially generate based like following certain distribution, these general adversarial networks. And I think it also ties in nicely with what we have with what we've talked about, because what you really look at in these generative models is also uh, you minimize the free energy basically. So, and these models allow you to generate images of people that don't exist, and if you have some certain like spoken like language data from a person, if I have a recording of you talking for 5 hours, I can feed that into my algorithm. That algorithm really builds a model of what your voice sounds like and how your voice functions and how you speak. And then based on this internal model, you can generate completely new output. you can basically generate a prediction in that framework of how it would sound like if you said something. And that makes it really is also going to have a big impact on our media landscape, because that allows you to simply generate a soundbite of a politician that you want to like create a smear campaign against. You can create a fake video of a person doing something embarrassing, for example. And this is all based on these algorithms and basically kind of the free energy principle and these things inspired by the brain as well.
Yeah, no, I used the same example when I was on stage a year ago. I mean, if for humans it becomes really hard to distinguish what is real and what is fake, bloody hell, then we have a problem.
Yeah. Yeah. What do you think we can do against these deep fakes? Do you have any ideas?
Now, I see companies that generate deep fake detectors. So we have to start building defense layers as well against this type of attacks. I think that's great to see that companies are actively also are aware of the consequences of this technology. And again, it's not stating about that the technology is good or bad. It's like a gun. It depends on who has it in his hands and how it is being used. But of course, the potential of this technology is far bigger than ever has been, because it can it's so easy to indeed, to your own words, make a deep fake and send it to so many people. It's or create a botnet that's or fake user groups and God knows whatever. Let's say the list is endless. So that's going to be a challenge indeed to start recognizing it and figure out how to find a strategy against it.
Do you think people like us working in AI research and in this whole area of neuroscience, AI, computer science, do we have kind of an ethical obligation to keep watching what happens with our technology? You mentioned the example of the gun. Like, is a gun manufacturer in a way responsible for what happens with a gun in the long run, or are we like should we still be curiosity driven and ultimately like be motivated by the ideals and try to focus on them?
Yeah, it's quite an interesting social dilemma. Of course, the answer is yes. But on the other hand, you cannot say, let's stop and let's ignore there is no atom bomb. That then simply somebody else will develop it, and you have a bigger problem. I think let's say you have to be conscious about it. You have to think, and agree to some measures. And I do believe with atomic weapons that could kill the planet, and we are as human race sensible enough not to use them. Hopefully, also not in the coming hundreds of years. But yeah, I'm pretty sure for AI, we'll also figure out a mechanism what we should do. And then there's all kind of movements, many forums, responsible EI, ethical EI, all kind of concepts are being developed. I think especially Europe is pressing forward, but also the US, etc. So I do believe that of course we still have to grapple with this topic, but it doesn't help to put your head into the sand and then just hope it goes away. That is not.
Yeah, that's very true. I mean, you already talked a bit about how you got into the like the mathematics and the field again after taking a longer break of mathematics and these kind of topics. Is there anything you can like specifically recommend to people new to the field and wanting to get into AI research, wanting to get into data science, wanting to educate themselves about the topic, like where to start, what to read, what to look at?
Oh yeah, absolutely. And as I said before, on the internet is also the beautiful forum where there's many and useful information that can get you started. I would argue just start and start, programming your first neural network. Just experience it and by that internalize it what it really means. go to Kaggle, and you'll find many starter courses to get started in the neural networks, and just start trying it out for yourself. It's not that hard. Frameworks like, when you at the start, a couple of years ago, you almost needed a PhD in TensorFlow to actually understand it. Now it's not needed anymore. Keras is integrated in TensorFlow. Even I can do it, so you can do it as well. I would argue it's quite straightforward to try and build a couple of networks. Try the Hello World MNIST for starters. Do a reinforcement learning by trying out to win a simple Atari game. Let's say it's all the stepping in is quite made quite easy. If you are interested in active inference, I think we referred already 10 times to my Kaggle notebooks. Have a look.
Yeah,
Uh,
yeah,
so, so just start over there. I really did my best to make it simple for everybody to get started. And let's say the only thing, of course, is it's kind of it's more difficult now to find the right let's say starting point, because there's so much on the internet, which one is the right one to start. But I would say try Kaggle and train the stuff in the cloud. Don't start build your own PC, or try to install and TensorFlow in Ubuntu, etc. All way too difficult. Just use a Kaggle notebook in the cloud, and it's all arranged for you, and you can easily start.
yeah. Maybe on a more like personal note, how has like, your experience in the business world helped you in any way with your PhD now, or is there kind of a fruitful collaboration between these two modes of thinking and approaching problems and thinking about the world?
Yeah, I think people often talk about the T profile. So in my whole business career, I've been busy to create a very broad roof of the T. To have had many roles and executive levels, of the T-shape, the horizontal roof part for me is now very broad, and that helps me. But of course, now in the science part, let's say the vertical T part, or let's say, has to be much deeper than I had. So it's both an advantage and a disadvantage. Of course, my advantage is that, let's say, the broadness to understand and to compare it with big IT programs or projects, where you take certain steps and certain approaches to structure things, and get to intermediate results. And the agile methodologies work in short cycles, and all these type of things make me self-motivating, self-propelling, self-organizing, all these beautiful words that you want.
Yeah.
And then, of course, my challenge then is the let's say the math and the probability theories, and the dynamical system theories, and to get deep and deeper into these type of worlds. There, for me, I see it always as a challenge. And in the south of the Netherlands, we have this saying, dat zullen we nog wel eens zien. That is roughly translates, we will see about it. And
Yeah.
then that means that's just motivation to get your teeth into it, and figure it out. And then, once you figure out, again, a very complicated math formula from Karl, then I'm actually quite proud of myself. Like, hey, bloody hell, I understand it. So you find your motivational moments to move forward, and have fun. There's one thing I can give everybody: just have fun in it, because that's a true motivational driver.
Yeah, it's also considering it's a theory that a lot of people say it's really hard to understand or you can't understand, and then like uncovering some part of that is really a beautiful feeling. And also seeing kind of a lot of different things light up. And I think especially for me with cognitive neuroscience and this whole theory of cognition, it's really, I mean, you are a cognitive system 24 hours of the day, maybe not in deep sleep, but it's just like everything is cognition, and it's so fascinating to just walk around in the world and read about these theories and then apply them to yourself and the way you see yourself and the way you see the world. I think that's something that's deeply motivating and
Oh, true.
driving.
I'm new to the world of neurosciences and how the brain works. So I'm listening to podcasts, reading books, etc., etc., and it's just fascinating world.
Oh yeah. Maybe as a last question, is there any? I think maybe the answer is already obvious from what we talked about, but is there just one scientific riddle that you could uncover? What would it be?
Scientific riddle.
Like, I mean, everything. Maybe like a scientific theory, like a scientific question, or
Oh, I let's say I'm what I'm actually working on. So I try to find the next enrichment to active inference or neural networks by combining both. For example, by deep active inference networks or combination of the action added neural networks. I think somewhere is a potential breakthrough in the next little step of trying to understand true intelligence. And I keep my goals very modest, so I'm not trying to invent the whole artificial intelligence. So I focus on early primal potential, let's say, live beings that could have been there, that have a simple actuator and a simple, let's say, sensor, and they need to survive, and they have some things that they can do, and how then active inference could have. Let's say contributed to the birth of repeatable instincts towards intelligence, and if I can contribute somewhere in that domain by applying active inference in a robotic type of setting, I would be most happy.
okay, yeah, that I definitely wish you best of luck with that, and thanks a lot for coming on the podcast. It's really enjoyed our conversation.
Thank you for asking me. Really enjoyed it.